Изоляции. Так что все будет.
Окей, понятно. А что, сейчас? Я на какой момент ее...
Нет, стоп. Нет, просто вот старт, а потом в конце самого паузу.
Окей. Okay, I will try to explain how this in English. I will try. I hope that you will help me if I should have some troubles with this. So the name of this course is K3 Surfaces. And I don't know. I choose this subject just because in this subject some algebraic theory and analytic theory interacts in a very nice way. So I decided that maybe this topic is nice to study after a standard course of algebraic geometry that I hope all of you try to study. Okay, so maybe today I will ask you some questions. I suppose that you know answers to these questions, but maybe, I'm not sure because I need to understand what I need to explain later and what I don't need to explain. Okay, so why K3 are called so? First of all, because there was three famous mathematicians, Kummer, Keller, and Kadaira, and today we will meet two of them. We will discuss Kummer surfaces, and I will say that all complex K3 surfaces are Keller. But Kadaira, the name of Kadaira we will also meet, but later. And the second reason why K3, because there is a second highest mountain, K2. It's not so high as Everest, but it's very difficult to climb on it. So this is why these K3 surfaces are called so. Okay, so now definition. So first I will define complex K3 surfaces. Just because in this course I will mostly work over C, I will try to give also some comments about a parallel algebraic picture, but mostly we will work over C. So complex K3 surface is smooth, compact, connected, complex manifold of dimension 2, such that second holomorphic differential of smooth compact complex manifold X, such that second holomorphic differentials are trivial, and also we ask that the first homologies of X is okay. This is just.
May you say it again about this omega 2?
This is just holomorphic forms of highest degree. Okay. So now we work with in a complex world. So there are holomorphic differentials, you know, yes. And so there is holomorphic tangent. So everything is smooth. There is a holomorphic tangent bundle. There is a holomorphic differentials, and if we take exterior 2 and exterior 3.
Yes, I got it. What is O X?
This is trivial.
Trivial.
Trivial line bundle on X. Okay. We want that canonical class of I will say this later of these complex surfaces is trivial. Okay. So the first thing that I want to say about this definition is that that X cannot be can be может быть непроективным can be non-projective with this definition. So projective here means that we have an embedding of X inside Pn, inside some projective space of some dimension. And with this definition, X can be non-projective. Okay? Yes, but maybe later we will discuss that X are always scalar. And we will need this because for Keller manifolds we have Hodge decomposition, and here we will have Hodge decomposition. But it cannot be projective, and today I will give you an example of non-projective complex K3 surfaces. Okay, and also maybe I need to say that general, we will discuss what does it mean later. General K3 complex K3 surface is not projective. So we will discuss moduli spaces of K3 surfaces and so on. And general, roughly speaking, is a general element of the moduli space of K3 surfaces. In general, will be not projective. Okay. So this was complex definition of complex K3 surface, yes, and also I want to say that of course this is an algebraic geometry course, so we will mostly be interested in projective K3 surfaces, but for Torelli theorem we will need non-projective too. So we can't avoid this analytic thing in this setting. Okay, this was the first definition, and now let me give an algebraic definition. Algebraic definition that will work over any field. Here, field is just complex numbers, and this definition will work over any field. Okay, we will say that a K3 surface over K is a complete non-singular variety. Here variety means separated geometrically integral scheme of finite type. Separated geometrically integral scheme of finite type over the base field over K is a completely singular variety of dimension 2 such that first, second holomorphic form kx over k are trivial. And the second thing is the same. Is that the first cohomology vanishing? Okay. Maybe I should say that complete here means that map to a spectre of the base field is proper, and non-singular means that cotangent sheaf is locally free of rank that is equal to dimension of this surface, so of rank 2. Okay? So here we mean Keller differentials. Okay?
Can you say it again about complete variety?
Complete, okay. What does it mean, complete scheme over K? This means that when we consider scheme over a base field, we always have this morphism, okay? And we want that this morphism is proper. Okay?
How?
Proper.
Proper.
Okay? And now I want to explain why these two definitions are related to each other. So first of all, in this definition, we will always obtain projective K3 surfaces. So with this definition, X is always embedded in a projective space of some dimension. Okay? Here, I have already said that this is not the case. We can obtain non-projective varieties. And now, how does these two definitions are related to each other? Как стирать пластик?
Среднюю кнопку. Если вы
Это
хотите
там еще очистить.
Есть вообще очистить? Нормально, если сейчас?
это одна половина.
Ну,
В
Прикольно.
любом случае можно отменить.
Отменить тоже. Ага, спасибо. Sorry. Okay. How does these two definitions related to each other? This is because I'm not sure how to pronounce this in English. Gaga principle.
Vega.
Okay, Gaga. Gaga principle of Serre. So what's this principle? This principle allows you to associate to any scheme X of finite type over complex number. The following thing, just complex space that is denoted by xn, x analytical, and underlying set of points of x analytic is just the set of all closed points. The set of all closed points of scheme X. Okay? And also we can associate to any covariant sheaf F in such a way that we can associate to any covariant sheaf F on X a covariant sheaf F on, and this association behaves well in the sense that, for example, to structure sheaf or X, this gives you just structure sheaf of X analytic. Okay, this is defined just for scheme, and for an analytical space, this is just functions, local functions on its analytic. And also two differential forms, two Keller differentials on X over K. We from Keller differentials on scheme, we will obtain holomorphic differentials on X analytic. Okay, it's of course all this is not obvious, but it's just principle that was discovered by Sierra. And there is a natural morphism. Morphism of ringed spaces from Xn to X. Блин, прикольно. Yes, and for X projective scheme, or even more generally proper, this leads to an equivalence of abelian categories of covariant sheaves. To an equivalence of abelian categories of covariant sheaves on scheme with covariant sheaf of the underlying analytic space. Okay, so this is an equivalence. So in particular, we will have an isomorphism of cohomologies. In particular, for any covariant sheaf. Yeah. Okay. And if X was a smooth scheme, we will obtain a smooth manifold.
If we start with projective algebraic scheme, then we obtain projective analytic.
Yes, I will explain this.
And if
now.
we start with just complete,
Then yes, we will obtain a projective analytic space.
okay.
So we'll now obtain an embedding from algebraic K3 surfaces inside complex K3 surfaces, and the image will be projective K3 surfaces. What does all this mean? This means that if we have an X is an algebraic K3 surfaces, then over C, then the associated X analytic space will be a complex K3 surface. This is clear? Right? Just because by definition and this equivalence of abelian categories. Okay, and in this way, we will obtain an embedding of algebraic K3 surfaces over C to complex K3 surfaces, and the image is just projective
Yeah, well, position. Why X analytical is connected, compact?
Just because we had proper scheme. We had a variety, so this was proper scheme. This was smooth, and
It's geometrically integral.
in geometrically integral. So this is a variety. So we will obtain a compact, smooth surface. And because of this isomorphism, and because of this, we will obtain that this compact surface is K3 surface. Okay. So the image is projective, complex K3 surfaces. Just because if we consider an ideal sheaf, so if we have an embedding, then we can consider an ideal sheaf of X in this embedding. This is a covariant analytic sheaf, and so the associated algebraic sheaf will give you an ideal sheaf of X inside Pn, so it will be algebraic. So all projective complex K3 surfaces are contained in the image of this embedding. Okay?
Can you repeat this argument?
Just because if we have a projective K3 surface complex, we can consider its ideal sheaf.
Yeah.
It's some analytic sheaf, and it will be algebraic just because it's inside Pn. So an algebraic, so this will give an scheme structure of X just because you consider OPN
Yeah,
or
but
an
why
algebraic sheaf.
such sheaf? Like we get some algebraic scheme, and why an identification of such algebraic scheme will be our first X.
Just because it's obvious, no?
Well,
Because we have this just one complex structure, I think. So I think this is more or less obvious. So, any question?
Maybe the point here is why IX analytic ideal sheaf is generated by algebraic elements.
Just because of this principle. If we have an embedding here, then we can give an algebraic structure on the corresponding scheme. Maybe it's better to give this as an exercise. So I explained how to solve this.
Вроде более-менее она.
Нет, мне кажется, тут все проще.
Я имею в виду, что...
Нет, это как бы не лемма, это просто это принцип.
Не,
ладно.
я имею в виду, почему пучок аналитический, он алгебраический на самом деле.
Потому что у нас уже есть вложение в PN.
Да, я и говорю, что это lemma Joe просто.
Ну хорошо, окей. Vadim said that this is a lemma Joe.
Чё?
Так. And now, what next? Yes, maybe now we need to discuss some examples. So the very first example is a smooth vertic. In P3. So how we can prove that this is K3 surface?
By adjunction formula.
This is about canonical bundle and about vanishing of 4x. How to prove it?
The projection formula. How to prove the projection formula.
How to prove that? So we want to show
Because it's rational.
x4 is equal to 0. I'm asking just because I don't know what I need to explain. No, I don't need to explain. So for this we can consider. So So what's here?
-4.
And how to prove now this thing?
Wrong exact sequence and compatibility or self-reference.
So we just consider the long exact sequence of cohomologies, and we obtain what? We obtain that on P3 x1 is equal to 0. And how to deduce from this that we have this vanishing?
Because the probability will push forward because it's an inclusion.
So you know, thank you. So everyone understand why we have this this equality, right? Yes, this is just a closed embedding. So this is an affine morphism. So if we consider so cohomologies doesn't change under this closed embedding. Okay. And now adjunction formula. What is adjunction formula? Только давайте не ты, не Саша. Все понимают, что everyone knows adjunction formula. Who knows? We see. Okay. Sorry, I just. So I just not sure what thing I should explain and what thing I don't need to explain. So this is the reason why I'm asking. If someone wants to see what is the adjunction formula and how to prove this, I will explain. Okay. So this is okay for.
Maybe it's okay if we skip it now.
Adjunction formula.
Yes. Because я, например, даже не знаком с языком схем, я прошу прощения, что я говорю, вот, поэтому я просто нагружаю потом, вот, возможно, те, кто не знаком с этой формулой, примерно в таком состоянии.
Хорошо, поэтому объясняем, да? Все нормально, что я объясняю. Окей. What is the adjunction formula? In this case, by omega x4, I will denote this shift, and in fact, this is a standard notation. Okay, just because it's shorter. So, what is the adjunction formula? It says that this shift is isomorphic to what? Is isomorphic to P3 or times what? And then we restrict this to x4. And now we will discuss how to prove this, okay? We all suppose that we have x inside y, so everything is smooth, and x is Cartier divisor. In y. Then we can consider the following exact sequence. We always restricts to So when we work with scalar differentials on a scheme, we always have this part of this exact sequence. This is the very first properties of scalar differentials. And here, when everything is smooth, this is in fact exact sequence. Okay? And now, what is this? What is this? How it's called this? This is a conormal bundle of x inside y. And what is in this case when we have a Cartier divisor? So they are associated with a Cartier divisor, we can associate a line bundle that is denoted by that is usually denoted O Y X. Okay. So what is the conormal bundle in this case? If we have a Cartier divisor.
It's OYX tensor to OY.
Yes. This is just OY, but
tensor OX.
yes. Okay. Mm-hmm. No. X. E. Okay. So this is clear or not? Just because ideal sheaf for a Cartier divisor, this is O Y minus X. So if we consider this thing, then we need to O Y X. And so this is how we obtain this thing, okay? And this is just a restriction of the corresponding line bundle to X, okay? So, and now how we can... как стирать-то? Ну, я выбрала ластик, он сейчас уберет это? О, отлично. And now how we can prove adjunction formula from this exact sequence and using this thing. What is omega?
The
Mhm.
highest exterior front.
Yes, this means that is equal to determinant what times minus x. Okay? And from this, and this is what is usually in my notation. This is omega omega y restricts to x, and this is omega x. So from this we obtain that omega x is isomorphic to omega y times
OY.
Нет. Ладно. Сейчас. OY what times OX yes, restricts to X. Okay? So I'm sorry, I understand that most of you know this formula and know how to prove this, but some of you don't know, so I explain the proof. Okay, and now how we can prove that this is a trivial line bundle. What is this? What is the canonical bundle of projective space?
O minus 4.
Mm-hmm. This is just 4. X4. This is just X4. Okay. Так, дальше поехали. Okay, and maybe I will also say something about complete intersections. Here. So the second example. А часов нету, да? Example 2. So this is complete intersections. In Pn. Suppose we have a complete intersection d1, d2, and so on, dn inside Pn plus 1. And suppose, what does it mean? This means that we just take divisors of degree d1, d2, and dn inside Pn and intersect them. Then this is a K-free surface. if and only if what is equal to what? If this sum by adjunction formula. Okay, and what does it mean? This means that we will have just three cases. The first case we discussed just now. This is quartic in P3, and 1 is equal to 4. Second is and this is a complete intersection of cubic and quadric. And the third case is just when we have 3 quadrics in P5. Okay? Just because of this equation. We can have just these 3 cases.
Can you explain why if the sum of dy's will be n plus 3, it will be k3 surface?
So I didn't, we will obtain, from adjunction formula, we immediately obtain that canonical divisor of this complete intersection is trivial, right? Just because we can, we proved a more general thing for every Cartier divisor inside. Okay, and just iterating this operation, we will obtain that omega is trivial. And now maybe let me say that this is an exercise because it's trivial. It's not difficult to prove. So let x in Pn be k-dimensional. Complete intersection. Then all its cohomologies vanishing for I greater than 0 and less than t. So this is an exercise. And in fact, everything that you need to prove this, we have already seen in the case of smooth quartic. Okay? Just by induction. So the second example is complete intersections in Pn. Here we have 3.
If it's harder equal than 4 here.
Then you cannot obtain this just because. Okay. And of course, we assume that are greater than 1, because otherwise this is just a hyperplane section of Pn, and we obtain P projective space of n minus 1 dimension, and this is a trivial case. Okay, so assuming that this is a non-trivial complete intersection inside Pn, we have just these 3 cases. Okay. And now let's discuss Kummer surfaces. That is algebraic. That is, we have an equation inside projective space. And here we don't assume this. Most complex torus aren't algebraic. So we start from this thing, and now on this complex torus we have an involution. Maps to minus t. And now we consider the fixed points. So this is points of order 2 here. And how many points, fixed points, we have?
6.
0, 16 points. P1, P2, and so on. be 16. And now let us consider the blow up. I will denote it like this. This is the blow up of this 16 points. And I will denote by EI the corresponding exceptional curves. Exceptional curves of this blow up. Okay, and then the involution I will extend to an involution of this blow up. To an involution of T, I will denote it by. And now let me consider just so we have an involution here, and now we just consider the quotient of this involution. I claim that this is a K3 surface. So what is the commutative diagram that we have here? So we start from complex torus, then we consider blow up. Here we have an involution. This is a quotient by this involution, and also we can consider this part of the diagram. We can consider we have an involution here. We can consider involution here. Okay, so and we will denote by pi the projection to x. Okay, and what is this? This is just double cover. Of x branched in 16 exceptional curves. Exceptional curves of the blow up. So here, so we have an involution here. We can consider quotient of this involution, right? Then here we will have 16 ordinary double points. Then we can blow up them. We obtain 16 exceptional curves, and then we can consider double cover of x branched along these exceptional curves, and this will be exactly t hat that was blow up of 16 points here. Okay, so we have this commutative diagram, right?
Excuse me, I have a question. How do we extend involution to the blow up? We act trivially on exceptional curves here.
Yes. And now, yes, and now what I want to prove is that this will be a K3 surface. Is a K3 these receivers. These are called Kummer circles. Circles of T. Okay, and now let me give a proof. So why X is smooth? I will explain a bit later because this is just a local computation, and I want to explain how we can define blow up locally a bit later. Or maybe everyone knows how to define locally blow up in coordinates. Everyone knows, or some of you don't know? Ты знаешь, Игорь?
Раздуть.
Да.
Вроде знаю.
No, who don't know how we can define blow up locally in coordinates? Okay.
Слушай, а можешь сказать еще раз, почему там 16 точек неподвижных? Я чуть-чуть соображаю.
Потому что мы берем фактор c2 мы берем точки порядка 2. У нас есть фактор c2. Тебе нужно посмотреть, какие у тебя точки будут лежать в решетке. Тебе нужно посмотреть, какие точки будут у тебя лежать здесь. Вот представьте, трехмерный случай. У тебя там будет кубик такой, восьмимерный.
Я понял, ладно. Четвертый.
Sorry, sometimes I will answer on question in Russian, but it's not difficult questions. Okay. So we will.
Сейчас, ну, условно, особую точку мы раздувая объемлющее пространство и потом пересекая, или нет?
Нет, here we will consider this blow up. So this is a
Здесь
smooth
да,
blow
а
up.
снизу справа.
Yes, but we will not use this because with ordinary double points there will be some, some problems with blow-ups. Okay, so this goes local computation. I will explain later. And now how we can prove, for example, that omega x is. So for this we will use two formulas. So first formula is what is the canonical bundle of the blow up of T? So how we can write down the canonical bundle of T from the canonical of T hat from canonical bundle of T? Everyone knows? You know, yes. Everyone knows this formula or no? Okay. Then I will explain how to do this. And here we just have sum of exceptional curves. And what is the canonical bundle of a complex torus? What is the tangent bundle to a complex torus? So if we take its dual, it will be trivial. If we take a determinant, it will be also trivial. Okay?
What is before omega t list?
Here is a pullback.
So we have some map sigma.
Yes. I will explain a more general formula later, a bit later. I hope that today, what is the canonical bundle of a blow up of a smooth variety inside a smooth subvariety of codimension K. Okay. So this is a particular case of this more general formula. I will explain after we deal with this proposition. Okay, this is the first case. What's next? And what is canonical bundle of omega t hat if we have a double cover, if we know that this has a structure of a double covering over X. What's this? This is the same thing. So when we have a double covering, we can compute canonical bundle in terms of the canonical bundle of X, but we also need to consider this term. This is so-called branch divisor, right? Okay, and now from these two formulas, what we get from these two formulas about
That's P upper star omega X is equal to 0.
is trivial, right? Okay. And now we want to prove from this that in fact omega X is trivial. How to do this?
So to show that pi upper star induces an embedding of Picard roots. Right?
Yes, but here I mean that embedded of Picard groups we will. Here is just projection formula in fact. To prove this, it's enough to have a projection formula. Okay, so let me say so. Okay, let me explain how to prove that. I'm not sure that I don't want to.
You mean you need a projection formula to prove that omega x is trivial?
Yes, now we know that this is. So far, we know that this is this fullback is trivial, and now we want to prove that omega x is also trivial. Okay, and to do this, so what is so what is this? What is the push forward of a trivial line bundle on the double covering to X? What's this? Do you know this formula? Нет, не знаю? Тогда точно обсудим. Окей. Значит, окей. Now I will give an answer, and after this proof, we will discuss just branched coverings of degree n and what is the. Ты знаешь, Саш, кстати?
Чего?
Вот это что такое? Нет? Ну вот, отлично, тогда все это обсудим. Okay, so this is X plus line bundle L.
Where the matter describes the branch twice.
Yes. This is I will explain a more general formula later. This is a how to say the square root of the branch divisor, right? Okay, where L without is a square root of here I denoted by E hat exceptional curves of this blow up. Okay. So so who knows this formula? One. Okay, then we will discuss this. Okay, great. So now using this formula, how we can prove that omega x is trivial? So for example, we can use projection formula, right? So if we take the thing, then what is this by projection formula?
It's omega x tensor p upper star of omega t. I suppose. So like omega x.
Mm-hmm. And on the other hand,
Just
we know
the-
that this is
just the lower star of omega t.
mhm.
Why we need this formula?
So and now we know what is this and what is this, right?
Why we need this formula?
Why we need this formula?
No, the upper formula for blow-ups.
No. Why we have projection formula?
No, for projection is to the upper formula.
What was this?
This.
This one? This is not for blow up. This is for double covering.
Yeah, but why we need this formula? Isn't it's obvious from this?
No. We just want to write down what is this and what is this, and then after this we will obtain that omega x is trivial.
Yeah, but do we know that P lower star of OT heads is locally free?
And what?
We know it.
What the upper star?
P lower star of OT heads is locally free.
Yes. No. This is what?
But this we know only from this formula, yeah.
Okay. This is for this is for double covering. What is the? Yes, we know that it's locally free, but how to prove from this that omega x is trivial?
Well, for locally free shifts we have like
Mhm. So just using this formula, we can write that this is OX plus L dual, and here we have omega x plus L dual omega x, right? And from this, we obtain that omega x is trivial. Okay? Mhm. And now how we can prove that H1 x or x is 0. For this, we can consider just embeddings.
Also, maybe I'm wrong, but I thought it was minus the range devising.
Yes, this is L dual, where R is the square. This is L dual. Yeah, everything is okay. So how we can prove this vanishing? So we have an embedding. Inside. Okay. How we can see that we have such an embedding? Just from this formula, because we have an embedding of OX inside push forward of OT, and this is not just an embedding. This embedding splits. So this is a direct summand inside this. So on the level of cohomologies, we will have an embedding. Okay, and for the blow up, for the smooth blow up, we have this. OT. Right? Just because there are no higher direct images in the smooth blow up, just because of O, just because all fibers are projective spaces, right? Okay. And now what's this? For a complex torus, what's this? Нет. Вы знаете? Нет.
Все логично, все очень Все.
Right? C2. This is just C2. Okay? We will. Okay, maybe we will discuss this later because. Yes, okay, we will discuss this later when we will discuss Hodge decomposition. When we will see that this thing is just isomorphic to global sections of omega global sections of T omega T1. Okay, so when we will have Hodge decomposition, we will immediately see that this first homologies of O is equal to the global sections of omega 1, right? And we know that. Okay. Okay, and here we know that tangent bundle and so cotangent bundle to a complex torus is trivial, right? And this is just C2 or times O. So this is just C2. Okay, but I didn't plan to give Hodge theory today. Maybe next time we will discuss this. But in any case, we obtain that this is C2, right? And what is the image of this embedding? We have here we have an involution, right? It's the same one, I. And the image of it's easy to see that the image of this involution is should be invariant under I, just because of the definition of X. This is just factor of this quotient of this convolution. Okay. So and what are invariants of this involution on C2?
0.
Yes, they're just 0. So from this we obtain this vanishing. Okay.
Can you explain why H1 X should be stable under involution?
No. It's not stable. It's C2.
Yeah, this
It's-
is C2. H1
yes.
XOX should be stable.
Yes, just because we take quotient here under involution, just by definition of X. This is a quotient on involution. So if you will see all these embeddings that we here and then here, you will see that as far as this quotient, we should the image of this embedding should be inside invariant part of this involution. Okay, just by definition of X. This is a quotient. Okay.
Yeah, and I want to ask, how did you use that omega X is equal to OX?
Okay, from this to think exercise. And now, let me maybe before, and now maybe I think it's a good idea to discuss all these formulas, I mean blow-up formula, and also to discuss something about double covariance and branch covariance, right? So maybe okay, let me first start from yes, and before I will explain this, let me say that what kind of K3 surfaces we obtained here. If T was an abelian surface, then X will be algebraic K3 surface. And if it's just complex torus that is not abelian variety, then the corresponding K3 surface will be is not algebraic. Okay, and in fact, in fact, it's not so easy to construct non-algebraic complex K3 surfaces in general, and this is the only case when we obtain them automatically. Okay. All other cases are quite difficult to describe. And now let me maybe start from branch coverings. Okay. Branch covering. So what is an? Let me first. Here we don't have an algebraic picture. Here we have an analytic picture. But for me, it's easier to remember algebraic one. And in fact, all formulas for algebraic case are the same as for analytic. So let me first explain branch coverings on the level of schemes. Okay, so suppose we have X, and suppose we have smooth, and suppose we have a line bundle on X, line bundle on X, and suppose that B is a Cartier divisor in X defined by Ln. Okay?
Where n is just sum.
Just sum, yes. And now let me consider the following OX algebra. We just consider direct sum of OX L minus 1, L minus 2, L minus N minus 1. And I will denote this by I claim that this is an OX algebra. Okay? And why it's algebra? Because this the structure of algebra is given by morphism L minus 1 to OX. That is dual to this defining morphism. Okay? So here we have a morphism from OX to Ln, and here is the dual one. Okay? So here we have an OX algebra. And what we know in algebraic word about OX algebra, what it gives in the theory of schemes. So this is an exercise in Hartshorne that affine morphisms in schemes are defined by OX algebras. So in this case, we can consider so-called spectrum of X of this algebra, and here we have a map to X, and then always the direct image of let me denote this spectrum by Y. The direct image of OY will be Rx. Okay? So this is an algebraic reincarnation, what we have discussed before. Right? Or do you know all this thing? Okay? This is how in algebraic word we define affine morphisms. This is something that is glued from spectrum locally. From spectrum of what? From spectrum of OX algebra. Okay, this is something that we can obtain. And this is for every affine morphism that we obtain from OX algebra, we have this property. So in particular, here we have OX and in the case of double covering, what does it mean?
Are you saying that all branch coverings can be written like this?
Algebraic, yes, I think.
I don't think so, but like, let's try an example.
Uh,
I think it's possible that some of the able to minus something and then you censor something.
No, what I said that in algebraic word, all affine morphisms are obtained in this way. No. I mean, all affine morphisms are obtained from spectrum of some OX algebra. This is what I'm saying. I'm not saying that all branch coverings are obtained in this way. What I said is that all affine morphisms in algebraic word are obtained from the relative spectrum of some OX algebra. Okay? Okay? And
one thing I'm confused here is that how do you get an morphism from OX to Ln?
what from what?
Upper right here. No.
Upper right.
Upper right.
Local section.
So how do you promise that Ln is say effective, that has a non-trivial local section?
So okay, let me suppose that this is an effective divisor, okay? Because we want to define branch coverings in an effective that branched in an effective divisor. Okay, I didn't say so. Let me say that here is an effective divisor. So we want to have this thing, okay? And I'm not sure. We have 10 minutes, right? Maybe in this case. So let me give. I will ask you to compute one thing, and maybe if we will have time, I will explain how to define all this analytically. So the last example is B x 2 here we have C double covering branched along smooth curve C along the smooth curve of degree 6. The first question is what is the corresponding algebra that I wrote here? What is this? What algebra we should consider? Here everything is algebraic, so P2 is algebraic. So what is the corresponding R P2? What is this?
So that just let L be 01 and your N is 5 here.
No.
Your N is should be 6 here.
Mm-hmm. But what is here? Minus 1. We want to have double covering. Yes. When we have double covering, what should we? This is an exercise just to understand what's going on here.
So do you mean that then that on the right hand side is just the degree of the covering?
Yes. This is the degree of the covering, of course.
Okay. Then over there should be O minus 3 and plus O minus 6.
No.
We're up, right?
Okay.
Yes.
So do you understand?
No.
No. Okay, this is an exercise. No, I mean that it's better to do this just. In fact, it's obvious. So we want to have a double covering branch in the divisor of degree 6. So we want to have that L minus 2 is equal to A minus 6, right? So this means that L minus 3, okay? So we can always consider branch coverings in an algebraic word that branched over some divisor. We can always consider double coverings that are branched over some divisor of even degree. So, right? So what we need here is just that this should be something even, right? And then we just take square root. So you remember we took square root from some bundle. So here we have this, right? So so we can write this as spectrum of okay. So and okay, and how to prove that this is a K3 surface now? So yes, and so what is, one more time, what is the direct image of OX in this case? Just by definition, right? The affine morphisms. And from this, what we immediately get about its cohomologies. So this is OP2 and OP minus 3. So all cohomologies vanishing, right?
First.
For first cohomologies vanishing. Here we have only just X, and this is OX, and this is 0. Okay, and this is because this is affine covering, and for branched coverings are affine, and for affine for affine morphisms we always have. So for affine morphisms, push forward is an exact functor, right? So we can compute cohomologies. So we have this isomorphisms, okay? Yes, and how to compute omega x? We didn't discuss this, but maybe I will. Yes, and this is trivial.
Why all three?
Just because we here we should take square. This is a consequence of a more general formula. Just because, so here we have 3, and here we also should have 3. This is trivial.
Yeah, but I suppose in when we discussed Kummer surface, we
Yes, but we use branch divisor over, and here we have here we use branched locus. It's called branch divisor and branch locus, right? So here we have something dull of branch morphisms, and when we discussed Kummer case, we consider branch divisor over. So there is a branch. So when we have x and y, we have branch divisor here and branch locus here. Here we use this one, and in Kummer surfaces we use here. So okay. In fact, I plan to discuss also analytic definition of branch coverings that maybe should explain how does this formulas with canonical bundles works, and also I plan to discuss a formula for canonical classes for blow-ups. So the first question is it okay if we will discuss this next time, or we just can ignore all these computational things? What do you prefer?
discuss next.
It's okay.
Next discussion.
Саш? Нормально будет, если я расскажу, да?
В смысле, конечно.
Ну, в смысле, ну как бы, ну хорошо, ладно.
Так нужно-то.
Is it okay if we will discuss this? Okay. Ну просто я пока, правда, еще не очень понимаю, как бы, кто что знает, кто что не знает. Понятно, что там Саша знает формулу применения, ой, я правда уже
Да, на меня вообще не забей.
Окей, хорошо, ладно. Okay, then we will discuss analytic description of double coverings and also some things. Next time. And I hope that we will start to compute some invariants of these surfaces next time. And I just want to show you that, so we have these nice formulas, and this is how we can prove them, and this is how we can compute things in algebraic geometry. This is the goal for the first maybe 3 lectures.
У меня просто там в РП2 второе слагаемое, это же по ОП2.
Ой, да.
Дядя, а мы будем доказывать, что
Я понимаю, что в этом решила, что все нужно обсудить с этим. Обычно они пишут, ну типа попросят, написано, ну вот. Да, поэтому вот, ну мне он завершается. В следующий раз я
Нет, спасибо большое за кумира, потому что я нигде не мог найти нормальное объяснение вообще, что там происходит.
Я сейчас дать раздутие, может, аналитически.
Спасибо.
Ничего не знаете? Ну вот Алекс знает. Sorry, Alex. It's okay.
I also don't know the reason why this is practices if the covering is cyclic.
Yes. I should say it is not transfer. I ignored this word cyclic and this is
I also don't know why this
okay, then we will discuss this next time. It's okay if I discuss.
Yeah.
I also thought it's important to discuss this
А вы как бы про книжки, которые в этом в описании курса рассказываете?
А что вы писали?
Там какая-то книжка есть. Какие-то книжки.
Ну, там есть Хойбрихт, да. Ну, там Хойбрихт эти формулы не доказываются. Почему я все это рассказываю? Потому что он говорит, ну, канонический класс считается так. Круто, спасибо.
То есть там как бы меньше объяснений.
Там не будет объясняться, почему прямой образ, там считается, что будет объясняться. Про прямой, поэтому я это с этим нахожусь.
Понял.
These ones are problems in action chapter.
Yes.
Or two.
What this is an exercise in hard score. I mean, for spectrum of я могу на английском, на русском говорить. В общем, вот это упражнение может быть.
Я видел, но
афинные морфизмы в хардскорне.
Там не должны предполагать, что они должны быть квазикоherentные вот эти алгебры.
Да, но я не сказала это просто потому, что здесь у нас...
Это автоматически.
Да, здесь у нас все это автоматически выполнено, а я хотела сказать только про циклические накрытия, чтобы не усложнять все совсем.
А циклические накрытия это...
Вот.
Это такие.
Can you give me some notes or books to read?
Hooybrecht is three surfaces, and also so here is the one thing that I try to explain to other students that Hooybrecht supposes that you know all these formulas. All formulas with canonical bundle of up, canonical bundle of branch covering, what is homologous, and so on. And I'm trying to explain all these basic things in this course. And I'm not sure where. So it's written in different books, and there are plenty of them, and I don't know the one book where everything. Of course, if you will solve all exercises in Hartshorn, you will Hartshorn, yes, you will understand all this again. But this is
Okay.
a big.
Thank you.
Это записывалось даже. А у вас не запись?
Что?
Это записано.
Я надеюсь, мне сказали, что записано.
Ну, вроде записано.
А, я не нажала на паузу, блин.